Many times you have to deal with aromatic compounds, and the spin multiplicity of aromatic compounds could be confusing, right? Could be. So let's this video will help you a little to differentiate between all those aromatic compounds. Okay. All right. Let's take a look right here. All right, first off, if you have a proton NMR, right, spectrum, how could you distinguish between mono and disubstitute benzene? Because we have first thing you have to be able to do this first because these have the mono and disub benzene have way different spin multiplicity, right? But if you can differentiate them at the beginning, it helps you so much. All right. First off, so how do you distinguish mono and disubstitute benzene? We usually go with integration. How many protons are on here on mono substitute benzene? 5, right? Normal benzene got 6 mono sub, so replace 1 with something else, so you got 5 protons left. The disub benzene got 4 protons, 4 protons, and 4 protons left. So the integration tell you right away. All right. So if your compound contain a benzene ring, look at the integration. You know it's a disub or monosub or trisub. How many protons are on the benzene ring? Right, and not just any signal. The signal around 7 to 8. That's where you're looking at. Okay. All right. So once you do this, so monosub, so we're done now. So but the disub though, they are 3 isomer. We have ortho isomer, so we have functional group next to each other. We have meta, so one carbon apart, and then para, so 2 carbons away. I mean, this is 3 carbons away. This is 4 carbons away. All right. So how could you differentiate between all these type of isomer? We have ortho, meta, and para. All right, start with the ortho. What's the spin multiplicity of HA though? One neighbor is a doublet, right? So a doublet. This I zoom in a little, you can see the jack in the middle. But anyway, it looks like a doublet. B is in between C and A, so 2 neighbors, a triplet, right? And C triplet, and HD is a doublet. So which means that if you have an ortho isomer, you're going to see 2 doublets, 2 triplets. All right. We're going to compare these splitting patterns with their splitting patterns of meta isomer. Okay. Start with an A. Any neighbors on A? What's spin multiplicity? No neighbors, just a singlet. Okay. B got 1 neighbor, so there's a doublet. C is between D and B, so that's going to be a triplet, and HD also a doublet. So a meta isomer, the splitting patterns you're going to see 1 singlet, 2 doublet, and 1 triplet. Okay, so different from the ortho, 2 doublet, 2 triplet. This one got singlet. Okay, last one. All right, so let's look at para. This one is easy. So either HA and HB. So what's spin multiplicity of these protons? A doublet each. So a para isomer, we have a double doublet. Does it make sense though? Right? So you can use this splitting pattern to differentiate between this type of the disubstitute benzene, ortho, meta, or para. Let's try. Let's get to try. All right, get the what we just learned to use. So I have 3 spectrum, 3 proton NMR spectra. So you have to match them. Is it ortho, meta, and para? All right, start with first one. All right, which one? Ortho, meta, and para. Well, this kind of clear. We have a 2 doublet, 2 triplet. This one ortho. Next one. So these are the blow up or the zoom in of just right here. We don't look at anything else because the proton on benzene is right here. You know. All right, we have look like this one. You see singlet right here. It might be jagged a little. It's fine, but this is a singlet. This is a real triplet, right? This is a singlet and 2 doublets. All right, so this is a meta isomer. We got a singlet right there. It's the only. Then go back right here. Meta isomer is only isomer that has singlet. All right, and one more. I think this one is clear. The para is the easiest one, double doublets. Okay. All right, this one. Next one. This one, just like you just look at it and tell me, is it ortho, meta, para isomer or not at all? Okay. Let's take a look. This one, so you can see this a zoom in of the spectrum. All right. So we have, you can see singlet right here. This is meta, obviously. All right. Now you may ask, hey, meta got so singlet, 2 doublet, and then a triplet right here. So where are they? Well, first off, we have singlet here, and we have 2 doublets. I have to draw this line to show you. This look like a kind of weird doublet. It's skewed a little, and we have a triplet, kind of weird triplet. Only because when the 2 signal really close, they kind of like they try to add up. Yep, there's a theory behind it why that happened, but we're not going to get to the detail. But it's just getting skewed a little like that when two signal are really close. Right? Anyway, so singlet, two doublets, and one triplet. Try this one. Oh, this one easy. This one's para isomer. Okay. This one was that. This one is ortho. If you're not sure, you can see that. All right, I'm gonna draw the line right here. Two doublet, two triplets at ortho isomer. This one, oh, this one easy. Para. All right. All right, next one. This one is meta. Right, so sometimes it's hard to see, but you just need to be familiar with it. All right, so we're gonna see singlet, two doublets, one triplet. Singlet right here. They're really close. Yeah. All right, try this one. This one. Oh, sometimes, most of the time, you can't really tell. This one is at ortho isomer, but you can't tell. I can't tell either because look at it, the peaks are jacked like that. Okay. All right, next one. This one is neither. Have you looked at the integration? There's a 5 proton on the benzene ring. This is a benzene right here. Don't look at anything else. This is a benzene ring right here. Right? There's a 5 proton. This is monostop benzene. Don't have to talk about ortho, meta, para isomers. Yeah, be careful. So you learn how to use integration. All right, we got one more. This one I'll tell you right away. So this one is para. You'll be like, hey, I don't see a 2 doublet. Right here, that's a 2 doublet. But again, when 2 signal really close, they kind of skew a little. They kind of add up like that. All right. We got one more. This one, I see singlet, 2 doublets, and 1 triplet, 4 protons. So that's one is para, or the meta isomers. It's singlet right there. Okay. All right. So we got a problem right here. I usually give it to the student, and many times students are debating between is it either one of these two. Okay. Now, so 4 proton right here. What do you think? This one kind of hard, right? But if I have to guess, this one hard. I can't tell either. But if I have to guess, I see a singlet right there. I'm going to go with this one, the only one that has singlet. The two doublets and 1 triplet, they might just like stay right there in the middle. Okay, so can't really tell. This one, let's say. This one is actually also a meta isomer. We have a triplet, doublet, and singlet right there, and a doublet right there. So singlet is a little abnormally high, only because of the this singlet and the doublet, the overlap. Okay, but I see singlet right there, so I'm gonna go with a meta. All right, that's the only way you can tell. Otherwise, you can't really tell in here. Okay, you just have to guess. This one, what do you think? Which isomers? Oh, this one easy. This one para isomers. Okay. Try one more time. This one. This one, if you see 2 doublets right here. Don't look at anything else. We talk about the proton on the benzene ring. Use chemical shift 7 to 8. Just these two. This is aldehyde 9 to 10. Don't look at it either. So just these two doublets. Okay. So if you don't get this, don't worry about it. All right. So this I show you may just help you to differentiate between ortho, meta, para isomer, and the monosubenzene and disubenzene. Most of the time, the proton of benzene have really close in chemical shift. You can't see all this spin multiplicity. All right. So, but sometimes if you could, it helps a little. So they just like give you in your arsenal. Just maybe you can use it. Okay. All right.